Thank you for having me again. It's a pleasure to be back at Bob. A few words about myself. I'm a consultant at TNG, and over my career, I've seen a lot of small and large-scale projects, from around 10 developers up to more than 100 developers, and I've seen them from different perspectives. As a software developer, as a product owner, from the architecture perspective, and also from the project management point of view. Beyond that, I am a Haskell and functional programming enthusiast, and I also organize MuniHack, a Haskell hackathon and conference in Munich. This year's instance is not 100% confirmed yet, but if you're interested, you can already save the date. So that's about me. Let's start with the talk. So I started learning Java when I was in high school, and I still remember my first Java Hello World. After learning C and getting stuck with the argc and the argv and the main method and pointers, it was refreshingly simple. And I still remember the commentary. Java is an object-oriented language, so we have to add a class around our main method. What a brave new world. But as my journey into Java progressed, I started to realize the main method is static. The class around that main method is never instantiated. It's nothing more than a namespace and global variables all over the place. So this example, nothing is really object-oriented about this example. And so my object-oriented love story was over quickly. I fell in love with Haskell. End of story. Well, of course not. I've been involved in a lot of OOP projects, from pure object-oriented programming with a dash of functional programming, like optionals and streams, up to really pushing the limits of what Java can do or could do at the time in terms of actual real functional programming. When I say there is nothing really object-oriented about this example, what is object orientation anyway? So one definition that I frequently came across, for example, in university, what do people teach in university, what object-oriented programming is? Usually you get something like this: polymorphism, inheritance, and encapsulation. Would you agree that this is the definition, or that this describes object-oriented programming? No? Okay, that's good. That's good. All right, so I learned this in university, right? So at least for a long time, I took this as gospel. But let's scrutinize these three terms a bit. So polymorphism. There are multiple types of polymorphism: parametric, ad hoc, row polymorphism, subtyping. When we are talking about OOP, we usually implicitly refer to subtyping polymorphism. Most functional languages, on the other hand, are based on parametric polymorphism, so that qualifier does really matter. And as we've learned from Andres in the morning, parametric polymorphism tends to make for good abstractions. Ad hoc polymorphism tends to lead to rather bad abstractions. And as we will see, subtyping polymorphism, for me, falls into the same category. It also rather leads to bad abstractions. Encapsulation, or the idea of hiding internal details behind external interfaces, is also something every somewhat modern language supports. Modules, libraries, abstract data types, all are examples of encapsulation. In the context of OOP, we are, of course, talking about class-based encapsulation. And yeah, in particular, usually in OOP, it's advised to keep data, the properties, internal to a class, and only expose behavior, the methods. If you've worked with larger OOP code bases, you know that a lot of times people just have the data and then add getters and setters. So essentially, they expose their data, their internal data, through methods. So nowadays, does encapsulation even matter? Or is it just vastly ignored anyway? And then there's inheritance. It was originally meant as a neat vehicle for code reuse, but then in the 1990s, the book on OOP came out, Design Patterns. We've seen the same book on Michael's slides as well. This book, also referred to as Gang of Four because of its 4 authors, is kind of considered the Bible of object-oriented design. And the authors gave us a simple recommendation for when to use inheritance, to avoid it, to favor composition over inheritance. So if inheritance has been deprecated for the last 30 years, should we consider it a defining property of object-oriented programming? And if so, what does that say about the state of OOP? Looking back at the definition, it is clear that we have a problem with either with OOP itself or at least with this definition. So the question is that really all that's to OOP? Well, of course not, as we will see later. But before we're talking solution, let's dive a bit deeper into the problems. So we're going to look at some examples of how these concepts lead to problems. Then we're going to revisit the question of what OOP at its core really is. And after that, we're going to talk about how I fell in love with object orientation again. So, has any one of you ever seen this class? Yes. So 10 years ago or so, when I started my career, this got passed around mostly as a joke on the lengthy name. Internal frame, title pane, maximize button, window not focused state, extend state. But I'm also going to use it as a starting point for my problems with subtyping and inheritance. And yes, this is old code, very old code, more than 20 years old. Modern Java code looks very, very different. But also, modern Java is not an object-oriented language anymore. Java has become a multi-paradigm language that also supports a lot of functional programming features. So just by looking at this file, we can't really tell what this file does or what this class does. How does this class differ from other states for internal frames? Is there also a title pane maximize button window not focused state for non-internal frames? Well, apparently not. No, there is none. I'm not entirely sure why. Most of the code in this class is not even in the same file because it inherits from state. So you'll have to look over there to see the rest of the implementation. And also, do we really need this to be a separate type? Because it's a class, you automatically introduce a type. Or why is it a separate class? Just by looking at the file, we have no idea what this class can or can't do. We only see the implementation of a single method. The rest is hidden away in the parent class state. And we have no idea where this method is in state is even called, if there are other methods in the class. The only thing we do know is that this method is not part of the public interface because it's protected. It's to be called internally. This brings us to the problem of inheritance, one of the core pillars of object-oriented language design, and also the one that we've known the longest that we should avoid it. First of all, inheritance breaks encapsulation. In order to override anything, you need to be able to access internal state and methods of that class. So in order to make a class extensible through inheritance, you need to expose your privates. And you have to strike the impossible balance between extensibility and encapsulation. I say impossible because this way a parent class effectively controls how it can be extended and how not. Exactly not what we want to have for reusability. Inheritance also leads to a tight coupling between parent and child classes. Since child classes access some of the internals of a base class, changing these internals in the base class may affect or may lead to changes in the child class. So we really have to treat those internals as part of the public interface if we want to make things extensible. The particulars of how overriding methods works in double dispatch languages also leads to a phenomenon that I like to describe as non-locality. Internal methods can deliberately jump up and down the class hierarchy, and you never can be exactly sure where in the class hierarchy you will end up, which method in the hierarchy will be called. Gang of Four, the book, already proposes a solution to this phenomenon to only extend abstract classes, or in other words, to only implement methods, never override them. All the problems that I've just described with inheritance were taken from the introduction of the Gang of Four book, which exactly leads them to their second principle of object-oriented design: favor composition over inheritance. But object-oriented inheritance is also tightly coupled with another concept, subtyping. When taking a closer look at the implementation of is in state, then we can see two things that are very, very widespread in Java code, and at the same time very widely considered anti-patterns. That's instance of and casting. Both are related, directly related to subtyping, and I would argue that by design you can't really get around them. First of all, the idea behind subtyping is to categorize objects like in the real world, just like Michael described in the talk before. We want to categorize objects like in the real world using an is-a relationship. A cat is an animal. An integer is a number. A Volkswagen is a car. The assumption is that most of the time we don't care what type of car we have. They all have a steering wheel, a gas pedal, brakes. So we want to handle cars as generically as possible. Problems arise when we have multiple conflicting taxonomies. They start, so in our case, we want to categorize cars by their brand, but we also could categorize them by their engine. And that starts breaking our clear hierarchies. We have to decide for one branch of taxonomy, otherwise we're going to run into the diamond problem. And in addition, we often enough do care about the specific subtype. For example, when you want to refuel your electric car at a gas station. But when you pass a specific object to generic code, you're losing that knowledge, and you only get something generic back. To illustrate, let's park our electric car in a generic garage. In exchange, we get a parking ticket, with which we can later get our car back. And when we do that later on in a totally different place in our code, then the knowledge of that specific subtype is lost. And when we try to charge our car, then we get a type error. Of course, we know what type of car that was. So we can apply that knowledge and restore the type information using a cast. And that is something you can't really avoid in the context of subtyping. However, as soon as you cast, you've already given up on type safety. Casting or type coercion means telling the type checker, trust me, you can't figure this out, but I can. I know better than you. And yes, there are programming paradigms and type systems where you can get very, very far without ever doing a typecast. In Haskell, the equivalent to a cast is unsafe coerce. It has already unsafe in the name, and it's very, very rarely ever used. So it's just with subtyping that you can't really get around this. One trick for working around this type error is to just add all the possibilities to the base class itself. We could add both charging and fueling capabilities to all our cars, and then just throw an unsupported operation exception whenever someone is trying to do the wrong thing. The this trick is quite common. The entire Java collections library depends on it. The collections API wants to provide maximum flexibility even with the base interfaces, which is very good at avoiding casts. Instead of providing dedicated interfaces for mutable and immutable collections, respectively, they just provide one big interface that supports both mutable and immutable collections, and then throws an unsupported operation exception whenever you're trying to use the interface with the wrong type. In subtyping polymorphism, there is a general rule how subtypes should behave. The Liskov substitution principle states that subtypes should not only be formally compatible, meaning they fulfill the interface, which is checked by the compiler, they also should be compatible in behavior. A canonical example is a square is a special case of a rectangle. So according to our subtyping rule a square is a rectangle, so square should extend rectangle. However, their behavior is exactly contrary. On a rectangle, we can resize the two dimensions x and y separately. On a square, this is not possible. We can only resize them together, which brings a dilemma. If we are resizing, so we could allow resizing x and y independently even for a square, but then it's not a square anymore, so we are breaking our invariant. Or we resize x and y together proportionally for squares, but then we are weakening the postcondition of the superclass, the postcondition that resize x only touches the x-axis and resize y only the y-axis. Or we get rid of the subtyping relation altogether. So just make square and rectangle completely independent from each other with no hierarchy between them. There is no silver bullet solution to this in subtyping. Well, there is one more option, the one that actually the Java collection API uses. If we don't promise anything, then we can't break any promises, right? So in the very definition of the interface for adding elements to a collection, to a mutable collection, the documentation says that this method may throw an unsupported operation exception. So this is very elegant. If the interface itself doesn't guarantee any postconditions, then those postconditions can't be weakened by implementations. Of course, this is also not a good solution to the problem. Essentially, this interface tells us that the method may or may not be there. That just shifts the problem even further to the runtime. So instead of getting a class cast exception because the types don't match, we will be getting an unsupported operation exception. Not a big win. So let's scratch that idea again and get back to the type level. Instead of adding all the functionality to our parent interface, we can also avoid type errors by checking that we have what we expect. That's what instance of is for. However, in OOP, instance of is also widely considered a code smell. And here's why. In OOP, program execution is driven by objects and polymorphism. Each object decides on its own how to execute certain functionality. So in OOP, it should not be necessary to inspect the class of an object from the outside because objects are abstract. This is completely unlike FP. In functional programming, program execution is driven by pattern matching. That is, by inspecting values and making decisions based on their constructor from the outside. An instance of does exactly that. It inspects the class of an object in order to make decisions from the outside. This means whenever you are using instance of, you've essentially given up on the principles of OOP. Instead, you've bought into a poor man's version of pattern matching. And yes, Java nowadays supports much more sophisticated instance of checks that are very, very close to actual pattern matching. But that's because nowadays Java is not an object-oriented language anymore. It has become a multi-paradigm language supporting lots of features that allow you to do functional programming. But even in classic object-oriented programming, there is a way to avoid these instances of checks. The visitor pattern. That brings us back to the book, Design Patterns. You can use the visitor pattern in order to essentially emulate functional programming pattern matching. There's other patterns that are just emulating functional programming concepts. For example, the strategy pattern just emulates higher order functions. In fact, I would argue that a design pattern is always a workaround for a feature that's missing from your programming language or programming paradigm. But if you're putting a lot of effort into emulating functional concepts, why not just use functional programming in the first place? Many of these patterns from Gang of Four are obsolete nowadays. The iterator pattern, for example, iterators are built into programming languages nowadays. The strategy pattern, Java supports lambdas and higher order functions nowadays. The visitor pattern, Java supports pattern matching nowadays. And that is because for the past 10 to 15 years, Java has evolved from a purely object-oriented language towards a multi-paradigm language. And that allows you to use the programming paradigm that fits the problem, which I believe is a good trait for a programming language. So far, we've gone through a very common definition of object-oriented programming, namely as polymorphism, inheritance, and encapsulation. And we've seen the problems associated with these concepts. But is that really the definition of object-oriented programming? Maybe we should ask the inventor of the term object-oriented, Alan Kay. In the late 1960s, Alan Kay worked at Xerox PARC and developed a new architecture or paradigm for programming, which he called object-oriented programming. In fact, the term object was already around at that time, but the object-oriented part, that was a term coined by him. And he developed the first language that used this paradigm called Smalltalk. So why not ask the authority himself? And in fact, some years ago, someone did exactly that, and the answer has been preserved for posterity. So you can actually look this email thread up on the internet. And it's very informative. So let's take a few minutes and see what Alan has to say. I should scroll on the other one, the other screen. Here we go. So what Alan has to say. First of all, Alan Kay explains his inspiration. Individual entities that communicate via message passing. Our modern concept of objects does cover the biological cells or individual computers on a network part rather well, but we will have to talk about the message passing part. He then goes on to describe his takes on polymorphism, inheritance, and encapsulation, and how he envisioned them originally. On polymorphism, he says, the term polymorphism was imposed later and isn't quite valid, although he also thought of having some kind of genericity based on algebraic principles. So we can really scratch subtyping polymorphism or polymorphism in general from our definition. The concept has been added later, but is not part of the original definition or idea. On inheritance, Alan Kay says outright that he didn't like it and that he intentionally left it out originally. So also the concept of inheritance was known at the time, was around at the time already, but he intentionally left it out. So also inheritance is not part of the original idea. And I think we can rightfully scratch it from our list of defining features. But if we get rid of most of the things that characterize OOP nowadays, what does even remain? Luckily, Alan Kay goes on to give a short and succinct definition of what he thinks OOP is all about. OOP to me means only messaging, local retention and protection and hiding of state process, and extreme late binding of all things. Now that is a definition we can work with. Only messaging is something we can directly add to our list. Local retention and protection and hiding of state process, I think we can actually keep this as encapsulation, as we will see. And we can add extreme late binding of all things as the third term on our list. So here's the definition of object-oriented programming according to its inventor. And now let's go through the individual bullet points to see what they really mean. The idea of message passing is, of course, taken from the inspiration of biological cells or computer networks. Objects should just exchange messages, and how the message is processed is up to the discretion of the receiving object. This is quite different from our modern notion of methods, which are really just subroutine calls on a procedural call stack with the additional scoping and dispatching rules. A much better match for message passing would be the messaging concept of actor models, where messages actually drive program execution, not a call stack. Local retention and protection and hiding of state process is a way of describing the concept of encapsulation. Objects have a local state, that's retention. The local state is not accessible from the outside, that's protection. And the local state is not even visible from the outside, that's hiding. And state process means that we're not only talking about the state, we're also talking about all the processes that govern this state. And in that sense, exposing local state via getters and setters should definitely be an anti-pattern, since it clearly violates the protection and hiding part. Now we come to the concept of late binding, which I think is the most underestimated feature of object-oriented programming. The broad idea can be characterized as follows. Objects should be as independent as possible from each other, and they should only connect at runtime. The benefits are, if one object stops functioning, it may not consume any more messages, but the rest of the system can keep running to a certain degree. And also, individual objects can be exchanged at runtime. You can see the concept of late binding in action, for example, with Java application servers, like WebLogic, if you remember that kind of thing. There you have shared libraries packaged as jars, which you can exchange during runtime, and the deployed services will pick up the new class definitions. That's late binding. But also the idea of dynamic dispatch of methods in inheritance hierarchies is a good example of late binding. The downside, have you ever seen a class not found exception or a no such method exception? These exist because of late binding, when a class or method that was assumed to be there during compilation may or may not be there during runtime. Now, what to make of these principles? Moving forward, I would like to argue that modern software architecture paradigms do follow these principles of object-oriented programming, just not in a way we'd expect when we hear the term object-oriented. Let's go back to the garage example interface from before. Behind this interface, you usually have an implementation that might be easy, but might also be very complex. And that implementation is abstracted by the interface. In the spirit of encapsulation and information hiding, we do not care about the specific implementation. In a microservice architecture, the same interface could look like this. In a modern microservice architecture, we encapsulate functionality in, well, dedicated microservices. These services communicate via protocols like REST. So instead of calling methods on an object, we're now sending and receiving HTTP messages. Now we are no longer talking about programming paradigms. You can implement this service in any language and any paradigm you like to. We are now talking about architecture paradigms. And I'd like to argue that this architecture paradigm fits our definition of object-oriented programming very well. So let's have a look. The only messaging part is pretty trivial. Just looking at our standard REST API, that's JSON messages over HTTP. But in addition to REST, there's also other options like asynchronous messaging via message brokers like Kafka. Note that this also gets rid of the everything is an object notion. When you have method calls, then arguments to those methods are usually other objects. So that's why everything is an object. Unlike method calls, these messages here are just structured data. They are not objects. You don't pass a microservice as an argument to another service. This one, local retention and protection and hiding of state process, is also pretty simple. One general rule of microservices is that every service should have a dedicated database instance that no other service has access to. They shouldn't share databases. And for the late binding part, in a microservice landscape, we can deploy individual services independently without having to stop the entire system. And if one service stops working, then it may not consume any messages anymore, but the other services can keep running, at least to a certain degree, and they will usually keep functioning. But we can go even further than that. Late binding also allows us to scale services deliberately. For example, auto-scaling based on load, or even spin up services only when we actually need them, serverless. And with container orchestrators like Kubernetes or Docker Swarm, we can leave the late binding part entirely to the orchestrator. So I think that OOP is not well suited as a programming paradigm, but I do think that it is well suited as an architectural paradigm. Let's use Conway's law to differentiate between the two. Programming paradigms are there to support people who work on the same code base. When you want to change something, you go into the code base and you change it. Architecture paradigms are there to govern systems that are larger than that. When you want to change something, you need to talk to a different team. You need to talk to a product owner. You need to get your issue prioritized. Let's have a look what properties we expect from programming and architectural paradigms, respectively. Within a team, within a code base, you want static predictability. That is, strong type systems, code completion, exhaustiveness checks. On an architectural level, we need the contrary. We need flexibility. On a code level, we want things to be cohesive. On an architecture level, we need loose coupling. And with that static predictability on the code level, we want to focus on fault prevention. Again, things like strong type systems. On an architecture level, we can't really afford that. So we rather need to focus on fault tolerance, late binding. And the object-oriented paradigm is very good at the things on the right. Message passing is good at providing fault tolerance. Late binding provides flexibility and loose coupling. For the things on the left, there are other programming paradigms that do a much better job. I'd like to circle back to type systems one last time. So Alan Kay actually states that he doesn't like, that he doesn't know of any type systems that aren't a complete pain. But as we've seen before, it's really the concept of subtyping that makes type systems a complete pain. And I personally believe that the success of dynamically typed languages like JavaScript and Python over the last 20 to 30 years is largely due to the fact that all the serious alternatives were based on subtyping. And therefore, well, a complete pain. And I think that the success we are seeing now of languages like TypeScript and Rust over the past decade, also Golang to a certain degree, which all focus on structural typing and parametric polymorphism instead of subtyping. That shows that these principles are really the better alternative as a programming paradigm. So we're coming to the end. Let's have a quick recap of what we've learned. First of all, we saw the common definition of OOP in terms of polymorphism, inheritance, and encapsulation. That misses the original point of object-oriented programming of the paradigm. We saw that polymorphism and inheritance are a disadvantage for programming paradigms. They get in the way of reusability, they get in the way of extensibility, and they make type systems less expressive, more complicated. The original idea of OOP in terms of cells that communicate via message passing fits well for modern microservice architectures. And we saw that this is actually a good analogy because the general principles of object orientation are well suited as an architectural paradigm and much better than as a programming paradigm. Ultimately, I believe that there is no one programming paradigm that's superior to all the others. Instead, I think that paradigms are particularly suited for one class of problems and maybe bad at other problems. Writing a compiler, you should probably use functional programming. Writing a front end, reactive programming is probably a good choice. Writing a monolith, object-oriented programming may be your best friend. In the end, it is best to have the ability to choose the paradigm that fits your problem. Thank you very much.
Thanks a lot. Yeah, questions?
So I have an anecdote for you.
Anecdote.
So many years ago, I was there for a conversation between Olin Shivers, who was famously dynamically typed, and Benjamin Pierce, who was statically typed. And both functional programming people, right? And they, and so it's a folklore in functional programming that you need static types for large software and not so much for small software, right? So Olin said something along the lines of, I like Scheme because it's easy to hack something small together. To which Benjamin Pierce replied, you're full of shit. Right? And I think you just agreed with him by saying that really as a programming paradigm, the static types help.
Yeah.
And as an architectural paradigm, maybe they're not so important.
Yeah.
Is that true?
Yeah, yeah, exactly. As a types do help. So when you have a group of people that work closely together, or even if you're working alone on a project, then usually you have something cohesive. You want to be able to quickly extend it, to mold it, to change it, and static types do help with that. Of course, if you're really writing a one-off script and you are sure that you're never going to touch it again, then maybe it's not that important. But as you said before,
I think static types are especially great for that. Right?
The long-term evolution of a software project, or even the long-term maintenance, is also something to consider up front. But then, yeah, then you have systems that are much larger than that, And there, I mean, first of all, types are not that useful because you're not collaborating as closely as before, and secondly, things change on a much longer time scale. So you can get away with having less expressive types and more. So I mean, your typical Open API documentation is also something like a type specification, right? But it's not designed to be expressive, to be quickly extensible. It is designed to describe the system well enough and to document it. And yeah, so you have the smaller a team, the more closely people are working together, in my opinion, the more you need or want to have expressive types.
More questions? Yeah.
So we should not inherit but compose
Yes.
objects. What would be this analogy for cars? So how would I build an electric car? Is that a microservice that gives me acceleration and another microservice that maybe provides the battery that can be charged? But how would those internal states communicate? So is it possible to really compose those things without exposing the internals?
To a certain degree, the way of how cars are built, and I mean in the real world, not how we model them in a programming language, but how they are being built really, is kind of changing right now. We used to build cars by putting lots of individual components together that communicate on a one-to-one basis. So you have a sensor for your parking. You have your parking sensor, and you have your drive-by-wire steering wheel and whatever, and they communicate in a point-to-point fashion. And in cars, actually, you can see the contrary right now, that cars are starting to get more integrated, or let's say the most successful car software paradigms right now are the ones where there is one operating system that governs all the sensors, and not so that you don't have that point-to-point communication that much anymore. So I'm kind of contradicting myself here, right? And again, it's a question of what you really want to reach with your architecture, what you want to focus on. And for a car, it's really important that all the data and all the functionality is governed in, well, as centrally as possible. At least for your core functionality, like your gas pedal and your brakes, you don't want to have them as individual entities that know nothing about each other. You want to control them together. So again, we're coming to the point that depending on what your goal, the goal of your architecture is, you want to use different paradigms.
For me to answer the question, there is no such thing as an abstract car. You can't build an abstract car.
Yeah, that's fine.
So no, I mean you can't drive it. So if you want to drive a real car, then of course you have to compose different parts. Mm-hmm. And so the interfaces, what matters are the interfaces between those parts. So you can perfectly buy a German car, let's say. And which would be the same car would be electric, and the other one would be gas powered. And in the fabrication and building of the car, they are assembling them by composing them, not inheriting them. Yeah. So in the sense,
a general construction of the product of two objects, so to say, like you just put those together, and maybe some of the methods match, and so they can exchange messages. Is there such a construction in OOP languages?
Not sure if I got the question correctly.
It's a composite.
Can you
It's a
repeat?
composite. You can hide the detail of the composite behind the interface that this component is exposed. And it's not inheritance, it's just composition.
Yeah.
I mean, by definition, composition and decomposition. So I think that's,
Yeah, you compose, essentially you compose your car from parts that are somewhat exchangeable. You have engines that where you usually have multiple engines that fit one chassis. You have tires that adapt to your to your rims, etc. So, in that sense, it is really composition that that governs this this architecture. Although, and as for inheritance, usually you have one outer specification that tells you if that part fits or not. You usually don't inherit from, I mean, in the real world, you don't inherit from anything usually. You have common parts. You don't take the part and add functionality around it or leave the functionality out, right?
Yeah, but you must have some kind of polymorphism, don't you? Like in the electric car, there's something that must provide torque. If you want to call accelerate, then you must have some component that provides the torque. Yeah, so either it's electric or it's combustion engine, but
Yeah, but polymorphism is not the problem. It's the subtyping,
Okay.
the subtyping part. You have lots and lots of other options for polymorphism, especially the structural typing part, for example, where you say, I want something that supports this thing. I want something that provides torque. I don't care what else it does. It just needs to provide torque.